Okay, guys, so we know the rate of change is the derivative, but we've got two different types of rates of change. The rate of change of something between 2 points, so if I had a point here and a point here, the rate of change, of course, is their gradient. And then secondly, I've got an instantaneous rate of change, which is actually at a single point what the gradient is or the tangent is at that point. So that's an instantaneous rate of change, whereas this here is an average because it's between 2 points. So in terms of real life, you can sort of think about it as they have what's called a fixed speed camera. So a fixed speed camera gets your speed at a point in time. And they also have average speed cameras. So they might take just say you're at a single point and you're traveling at 87 kilometers an hour. And then you get to another point and you're traveling at 94 kilometers an hour. If the speed limit's 90 kilometers an hour, you might not get booked because in between here, that's what matters. Because they're trying to work out what your average speed is over that time. So what they do is they find out your distance over your time that it took you to travel from this point to this point, not your instantaneous speed, but what you're averaging over that time. And then they might say your average speed was 89 kilometers an hour, because you might have gone 87 kilometers an hour, 86 for a while, 88. Someone might have pulled out in front of you and made you mad, so you sped up only at this point. So they go, oh, over the average, you're actually only doing 89 kilometers an hour, so you're not doing anything wrong. Your average speed is below the speed over that whole journey, so they don't book you. But if they took your instantaneous speed, if you were doing it at the wrong time, you would get booked, which is sometimes it's a bit unfair because you're just unlucky. Okay, so your average rate of change is your change in y over your change in x. So if I said x goes from 2 to 3, so that's my interval, 2 to 3, we've got to work out what y goes to. So if I put x equals 2 into that equation, so I'm going to write out the points. I've got the point 2, and when I put 2 in, I get 4 plus 4, which is 8. When I put 3 in, I get 9 plus 6, which is 15. Now your average rate of change is your gradient between those 2 points. So your change in y is 15 minus 8. Your change in x is 3 minus 2. So in this case here, our average rate of change is 7 over 1, which is 7. So it means that average gradient between 2 and 3 is 7. So as you move 1 right, you go up 7. Okay, so that's the average between those 2 points. Now, if I graph that graph, x squared plus 2x, if we sketch it, and we want it between 2, so there's 2 somewhere there, and then 3, you can see it's quite a steep gradient because we go from 15, which is there, to 8, so 8 to 15, so we go across 1 and up 7, so average gradient over that interval from 2 to 3 is just 7. Okay, now it says to find it between the interval 2 and 2 plus h. So when x equals 2, we know that y equals 4 plus 4, which is 8. When x equals 2 plus h, we've got to put that into that equation. So we get f of 2 plus h is equal to 2 plus h squared plus 2 times 2 plus h, which is 4 plus 4h plus h squared plus 4 plus 2h, which we know it is h squared plus 6h, and then plus 8. So our other point is 2 plus h squared plus 6h plus 8. Now if I want to find the average gradient between those 2 points, average rate of change, it's our y2 minus y1 over x2 minus x1, which is, they cancel, the 8's cancel, so I've got h squared plus 6h on h. I can take out a h on top, h plus 6 on h, and they cancel. So my average rate of change is just h plus 6. So whatever h is, i.e. whatever the distance is away from the point 2, so just there's the point 2 and that was the point 3, that distance we know is 1. So if we put 1 into that, if we put h equals 1, we get our average rate of change is 7, which surprisingly is what we got back here, because they were 1 apart. If I was 2 apart, so if I went further away at 4, I'd put h as 2 into here because it's 2 away from 2, and then I would get my average rate of change is 8. So your gradient between 2 and 4 is equal to 8. However, this says here it wants our instantaneous rate of change of f with respect to x when x equals 2. So we know if there's our line, there's the point 2, here's the point 2 plus h. Now, we've found the gradient between 2 and 2 plus h, but if we want to find the exact gradient, i.e. the gradient at this point, our h value, h has to get smaller and smaller and smaller, so we say the limit as h approaches 0 of h plus 6. So we want h to approach 0, because eventually we'll get the exact gradient at the point 2. In this case, as h approaches 0, we get 0 plus 6, which is 6. So our exact gradient at the point 2 is 6. And we can do it using calculus. dy dx equals 2x plus 2. dy dx at the point x equals 2 is 2 times 2 plus 2, which is 6. So that's our instantaneous gradient using calculus. And this is our instantaneous gradient. It's also basically using calculus because we're using the concept of first principles to work out what the instantaneous gradient is at x equals 2. Okay. Here we've got a balloon that develops a microscopic leak and will decrease in volume. Its volume at time t seconds is given by that function. Find the rate of change of the volume at t equals 10 seconds. So I want to find the rate of change. So I want to find dv dt, because that's a change in volume over the change in time, which is negative 10 minus 2t on 100, which we know is negative 10 minus t on 50. And we want it when t equals 10. So given t equals 10, which is negative 10 minus 10 on 50. So it's negative 10 and 1/5. Now volume is in centimeters squared per second. So that's how, sorry, stupid question. I just looked there. Our volume is in centimeters cubed, and then that should be in cubed. Okay, for how long will this model be valid? Well, the model will be valid as long as the volume is positive. So as long as v is greater than or equal to 0. So in here, if we find it when v equals 0, 600 minus 10t minus 1 on 100, t squared equals 0. I'm going to multiply through by negative 100. So we get t squared plus 1000t minus 60,000 equals 0. Okay, what are we going to get? T squared minus plus 1000t minus 60,000. we can complete the square. T squared plus 1,000 T. If we halve 1,000, we get 500. If we square it, we get 25,000. I've added 25,000 on, so I've got to subtract 25,000, and I've got minus 60,000 equals 0. Okay, so we get T plus 500 squared, and then minus 85,000 equals 0. So we'll get T plus 500 is equal to plus or minus the square root of 85,000. So T is negative 500 plus or minus square root 85,000. It can't be negative, so it's got to be T equals the square root of 85,000 minus 500. So that's the highest value that it can be. The lowest value is going to be T equals 0. So we would say T 0 is less than T, which is less than root 85,000 minus 500. Bit of a stupid question, but anyway. Okay, this question's pretty cool because it's got to do with exponentials and a stove cooling. A pot's taken off the stove, and then we want to see what happens to it, like how does the temperature drop with respect to the temperature around it. And this is actually a real model. We use it in specialist maths called Newton's law of cooling. So I've got a temperature that's 80 degrees when I take it off the stove. It's placed on the kitchen bench. The kitchen, it's 20 degrees in there. The temperature can be found by this model. So this is your temperature at any time. So it says find the rate of change of temperature with respect to time in terms of T. So it doesn't want it in terms of little t, it wants it in terms of big T. So first thing we've got to do is find the derivative. So we say dt little t, is equal to, if we derive 20, we get 0. If we derive this, we bring our 0.3 down to the front, so negative 3 on 10 times 60 e to the negative 0.3 t. Of course, that'll cancel that to make it a 6, so we get negative 18 e to the negative 0.3 t. Now, it said it wants it in terms of big T, but at the moment it's in terms of little t. So what we've got to do is rearrange this formula to get this by itself in terms of big T. So we start off with T equals 20 plus 60 e to the negative 0.3 t. 60 e to the negative 0.3 t equals big T minus 20, because we bring that 20 to the other side and subtract it. Then we divide the 60 to the other side, so 0.3 t equals t minus 20 on 60. So now we can replace that into this formula here. So you get negative 18 times t minus 20 on 60, which is negative 18 on 60 t minus 20, which we know we can simplify down to be 6 goes into 18 3 times, it goes into 60 10 times, t minus 20. So that's our rate of change. dt is equal to negative 3 on 10, t minus 20. So you can see here your rate of change with respect to time is also your rate of change with respect to temperature. It depends on what the temperature is as to how the pot's cooling, and it makes sense because the temperature is dropping, our rate of change is decreasing, like it's negative. Now I can find the rate of change when t equals 80. So we put 80 into this equation. So we get dt is equal to negative 3 on 10, 80 minus 20, negative 3 on 10 times 60, which is negative 18. Now it is degrees Celsius per minute. So that's how quickly it's dropping after, when the temperature of the the pot is 80 degrees, it's cooling at 18 degrees Celsius per minute. So it starts off cooling down really quickly, but I think it'll slow down once we get to 30. So let's try that. dt given big T equals 30. So we get negative 3 on 10 times 30 minus 20. Negative 3 on 10 times 10. So when the pot is 30 degrees, it's cooling at negative 3 degrees Celsius, because they cancel. Degrees Celsius per minute. And it makes sense, it'll start cooling down really quick, but then it'll take a bit, like it won't cool down as quick as we get closer to the original temp. Okay, so that's what it means by in terms of T. Okay, last thing, motion in a line, they don't really do it that much. I've never really seen it in an exam at all, but this is a just in cases. So a point moves along a straight line so that its distance x centimeters from a point O at any time is given by that formula. Now, let me just explain the concept of distance, displacement, and velocity, speed. They're two different things. So if I travel from, let's say there's the point 0. If I travel over here, which is 2 meters away, and then I travel back, my distance traveled is 2 meters plus 2 meters, which is 4 meters. My displacement is 0 meters, because I'm at the same point where I started out. I haven't changed. So I've gone 2 that way and 2 that way, but I'm back at where I started. So displacement has direction because I've got plus 2 and then minus 2, so they cancel each other out. Whereas distance, we don't care about the negatives. All we care about is how far you've actually traveled. Now that's where velocity versus speed comes in. Speed is distance over time, whereas velocity is displacement over time. So if this took you 5 seconds, my average speed is 4 meters per 5 seconds, or 4 on 5 meters per second. But my average velocity is my distance traveled, which is 0 meters per second. Because whilst I'm going 2 meters a second this way, or 2 meters nearly a second, when I come back, it cancels it out. So my average velocity, because velocity has direction, like it knows the difference between positive and negative, whereas displacement doesn't, my average velocity is just 0 meters per second. Okay, now the next thing to bring into it is if you have displacement, so displacement is x is your displacement. If you derive displacement, you get dx dt, because your displacement is in terms of time. So when you derive it, when you get dx dt, that is your change in displacement over your change in time, which is also your velocity. So your velocity is v of t, which is dx dt. So if you derive your displacement, you get your velocity. And if you derive your velocity, dv dt, that is your change in velocity over your change in time. That is your acceleration. So our acceleration, a of t, is dv dt. or derive x twice with respect to t. So derive your displacement twice with respect to t. Okay, so let's try and make some sense of that. A point moves along a straight line so that its distance, x centimeters from a point, is given by that function. So this is our displacement at any time, like how far it is away from the origin. Find the time and the position it will have zero velocity. So we just worked out that velocity is dx dt. So I've got to derive this with respect to time. So I get 3t squared minus 12t plus 9. Now, find the time and position that the point will have zero velocity. So if I want my velocity to equal 0, 3t squared minus 12t plus 9 will equal 0. Of course, we can take out 3 as a common factor and divide it to the other side. So we get t squared minus 4t plus 3 equals 0. And then we get t minus 1, t minus 3. So t equals 1 or 3 seconds. So that's when our velocity equals 0. Now, velocity equaling 0 is when something's turning around. Because if you've got a velocity in this direction, as it turns around, so here it's positive. When it gets to here, it turns around. So this we have 0 velocity because it's turning around. And then it goes back the other way and it's got a negative velocity because it's going relative to the origin. Here it's going away from it, so it's positive, and here it's going towards it, so it's negative. To the right, positive, to the left is negative. Okay, and it says position. So we want to know x of 1, because that's when it equals 0. So x of 1 is 1 cubed minus 6 times 1 squared plus 9 times 1, which is 1 minus 6 plus 9, which is 4. So when the velocity equals 0, it's 4 meters to the right. Then when the time is 3, we get 3 cubed minus 6 times 3 squared plus 9 times 3. 27 minus 6 nines are 54 plus 9 threes are 27. That equals 0. So if we were to put this on a timeline, I'm going to say, here's my timeline. There's our origin. So this is when it's 0, when x equals 0, when t equals 0, sorry, when time equals 0, my displacement, x equals 0. So this is my starting point. Okay, after 1 second, it's at the point 4. Right. So after that's at 1 second, it's at 4 meters, and it's turning around because its velocity is 0. Then, so it goes from here, and then after 3 seconds, it's back here. Because it was turning around at that point because it had 0 velocity. So it's gone back, and then after 3 seconds, it's at 0, and it's also got 0 velocity, so that means it's turning around again. So 3 seconds, it's at 0 meters, turning around. So then anything after 3 seconds, it's going to go that way. Okay, it says to find its acceleration at those times. So if we know what our velocity is, v of t is equal to 3t squared minus 12t plus 9. A of t is the derivative of that, so it's 6t minus 12. Now we want its acceleration at that time. So acceleration, a of 1 is going to be 6 times 1 minus 12. So acceleration is negative 6 meters per centimeters, because it's centimeters. centimeters per second squared. And acceleration at 3 is 6 times 3 minus 12, which is 18 minus 12, which is 6 centimeters per second squared. So here, when it gets to this point, its acceleration is negative because it's turning around. And here, when it's coming up to here, its acceleration is positive because it's going negative and then it turns back positive. So its acceleration is positive because it's trying to turn it around. Okay, its velocity when its acceleration is 0. So acceleration is 6t minus 12. So I'll do it up here. Acceleration is 6t minus 12. We want its acceleration to equal 0. So therefore, 6 times 0, oh, that's not a 6. 6 times 0 minus 12. Sorry, I just stuffed that right up. 6t minus 12 equals 0. So t will equal 2 seconds. So that's when its acceleration is 0, which is going to be somewhere between here and here. Right, so it's going to be somewhere between that point and that point, because that's 1 second, and that's 3 seconds. Okay, and we want to find its velocity when its acceleration is 0. So we want to find the velocity when t equals 2. So velocity is 3t squared minus 12t plus 9, which is v of 2 is 3 times 2 squared minus 12 times 2 plus 9. 3 times 4 is 12 minus 24 plus 9. So I've got 21 minus 24, so negative 3 meters per second. So when its acceleration is 0, its velocity is negative 3 meters per second. Okay, that's a nice short, well, it's a nice start to kinematics, but like I said, they don't really do anything with velocity, displacement, and acceleration in Year 12 methods. It's mainly in specialist maths.